Welcome everybody to a super exciting episode of Parity Delivery Services Learning Sessions. Please forgive us with the technical difficulties. This is our second time doing a Twitch stream, so we had to get all our hamsters on their wheels and running really fast to make it work. But I think we got it going, and we're going to dive right into it. So welcome. My name is Joran. My partners Artur and Abhishek and I are going to take you on a journey through Pallet, timestamp, and talk about what inherents are. And this is all a part of a series of sessions that we've been doing that cover the 50+ pallets that are in Substrate's framework, as well as talking about some of the tools that we've built at Parity around the blockchain and to support the community. So to give you a brief agenda of what we're going to talk about today, we're going to briefly cover what an extrinsic is, just in case you hadn't heard that term before. We're going to drill a little bit deeper and talk about some what inherents are, and then we're going to get into the meat of things and talk about what timestamps are and why we need them for the blockchain. And then we're going to show you a demo and do a code walkthrough, and then you guys are always welcome to ask questions. So if you have questions while we're speaking, drop them in the chat box. So you don't have to wait to the end, but there will also be a Q&A at the end. Okay, let's get into it. What are extrinsics? You might have heard this term thrown around in this ecosystem. This was actually one of the first terms that kind of like threw me for a loop. I'm like, what's an extrinsic? But essentially, it's our fancier way of calling a transaction. But there is a slight difference here. So essentially, extrinsics are outside information coming into the blockchain, and they carry the instructions that a user wants to give a Substrate chain's runtime to perform their desired actions. So this is passed in, and it's not intrinsic. It's not coming out of the blockchain. It's coming into the blockchain. And there are three types of extrinsics. You have signed extrinsics, or rather signed transactions. You have unsigned transactions, and then you have inherents. So we're going to talk about each of those, and then we'll dive deeper into what inherents are. So signed transactions are probably the most common extrinsic that you're going to come across. Essentially, anything you want to do is going to require an extrinsic assigned transaction. These are instructions coming from an address that actually has the native token or a sufficient token balance that can be used to pay for the execution of those instructions. And this could be your most common case is probably a transfer event. If you want to send tokens from one account to another, you submit a signed transaction with all the instructions saying how many tokens, so on and so forth, to what address, and then you pay for that execution, and it works. Similarly, with like conviction voting, batch transactions, all those kind of quote unquote normal actions that a user would do would come through a signed transaction. Next, we have unsigned transactions. This is for special cases when the user doesn't have those funds in their account to pay for the execution, but they still need to perform an action. And this is a special case because we don't normally want to be executing instructions without having to pay, but we found it useful for very specific use cases. One being when Polkadot system was just getting booted up. Nobody had tokens. The token generation event hadn't happened, but we had a previous sale that was conducted on Ethereum. And so in order to claim those tokens, to get tokens for the first time on the Polkadot network, you needed to submit this unsigned transaction that released the tokens that you were owed, that you purchased during the sale. And then after that, you had tokens in your account to pay for transaction fees. And so then you would normally use signed transactions. Another example of where unsigned transactions are used is if you're a validator, you need to submit a heartbeat message to let the network know that you're still alive, still participating. And this normally comes through an unsigned transaction as well. Now we get to the meat and potatoes here. We're talking about inherents. This might be another term that you hadn't heard before, but inherents are unsigned pieces of information. So they're similar to previous unsigned transactions in that way, but they bypass the transaction queue altogether. So signed transactions, unsigned transactions, they normally go into the transaction queue and get executed based on the rules there. But inherents are pieces of information that bypass that queue, and they get added to the block by the validator that is producing that block. And they don't need to go through the regular transaction queue for that. And the super important thing, the purpose of this talk, is to talk about timestamps, and that is an inherent. There's also another inherent called parachain validation data, and this is also included by the validator producing the block, and it passes the information from parachains to the relay chain so that they can receive the benefit of the shared security model. So we need to validate the data coming from parachains, and this is passed through inherents. But today, we're talking about timestamps. So let's take a deeper dive into what timestamps are. As the name suggests, they are moments in time that are inputted into a block. And they are in the form of Unix time format, which I'm sure many of you have heard before. And they're included in every block. And but what is the purpose of having these things? And it's actually very crucial that we have timestamps. So let's take a look. So first of all, a very rudimentary level, humans like to have things in chronological order so they can see things and reason about history. And so timestamps at a very base level allow us to do this. They give us a chronological timeline to look back on and see what events happened in what order. And you can, I'm sure many of you have visited a block explorer, and it's always nice to see not only block numbers in sequential order, but it might also be interesting to see the actual date and time that certain actions happen. I know particularly for tax reasons, this is important too. What else do timestamps do? They help validators stay synchronized, like these lovely synchronized swimmers here, and ensures that they can come to consensus on what the quote-unquote real time is from the perspective of the blockchain. We might know that because we're in a decentralized space where we have nodes, computers all around the world sending information to each other, that information doesn't travel at the speed of light. There is some latency that happens, and for this reason, it becomes difficult to make sure that everybody is kind of looking at the same, looking at the blockchain with the same perspective. And so timestamps help keep everybody agreeing on what the real time is, at least within the perspective of the blockchain. Now we're getting to some of the more critical pieces here. Timestamps help to ensure that the blocks that are being created happen at least no faster than the target number of seconds. So this is the target block time that we have, and we're aiming for 6 seconds right now. And so if a validator were to come along and propose a block that happens less than 6 seconds from the last block, it's not going to be accepted. And this also, we also want to make sure that we're aiming for 6 seconds and not too much longer. And there's a whole kind of rabbit hole you can go down with how this is achieved, but that might kind of take us away from the topic of the day. But yeah, timestamps. We aim for 6 seconds here. And all of these pieces kind of come together to really highlight that timestamps are super critical. If we don't have timestamps, then essentially Polkadot as it is today would not function. And we're going to see what that means, or like in a very practical sense, how important timestamps are when we get to the demo and walk through further, which I'm going to pass off to Artur right now to take it away and do that demo.
Hey, hi everybody. So yeah, let's go through a demo here. We created 4 scenarios here to show you. So, sorry. Yeah, the first one is like, what if we just block timestamp from being updated on every and each block? So I'm showing some piece of code here, but Abhishek, our next presenter, will go deep diving into this. So yeah, but feel free to keep asking questions on the chat. So for this first scenario, what we did was created a new extrinsic. It's called block. And yeah, just creating this flag here and adding this check, this if check here. So if the new logic is blocked, we will just return OK without updating the now storage is where the current timestamp has to be in. So let me just run this. So, and Polkadot.js should be, yeah. So here, yeah, here the chain is healthy and producing blocks. So that's cool. We have the chain state here, and just checking the now here, what is in the current timestamp pallet storage. So things are okay. So what if we decided to use that block extrinsic? And yeah, block yes. Just submitting. And okay, so the extrinsic just got in the block 6. And as you can see, we just stopped producing blocks and the time keeps going, but no blocks are being produced. And if we check the logs of our node, we see a panic here. So yeah, timestamp must be updated once in the block. So that's expected. And yeah, that was the first scenario. And let me go back to this next one. And yeah, this is where the panic reaches this code. Timestamp must be updated. So yeah, this on finalize inside the timestamp palette. So yeah, the next scenario is like, what if we just set now from the timestamp to 0? So same kind of logic. We have the block again, but if it's block, we just put 0 inside now, and we tell that thing was indeed updated. So let me just run the second one and Polkadot.js. Okay, so let me refresh this, guys. Yeah, it's producing blocks. So yeah, again, everything's fine. So yeah, let's send the same extrinsic that we created. Oh yeah, just checking it again. Everything's fine. So timestamp now is working. So let's just 0 it. And yeah, this time we start sending 0 from the block 7 on. And as you can see, we lost the track of the last block time, but we keep producing block. And that happened because our node is fetching the timestamp from my OS and not from the latest block. So yeah, if we check here, we see that the timestamp now is 0. So Polkadot.js is not able to track it here. But yeah, again, this is kind of not that crucial. At least we don't get any panic here. So we can kind of unblock this. And yeah, the extrinsic and should be 16. Yeah, the 16 now, as you can see, we get everything like back working as expected again. So yeah, and an interesting thing here is that, like I said, from I think it was like maybe 10. This is the block 10, and we indeed got the correct timestamp here. But again, that came from my OS, my Linux OS. So that's why the chain was keeping producing and validating blocks. So yeah, and let's go back to the presentation. Okay, the third scenario is, what if I need to, I want to just create a new inherent data. So we decided to pick the remark palette here and created this store to, because we have the store one there. So we just add this store to extrinsic, and we created it as an inherent, how can I say, an inherent and ready extrinsic. So Abhishek will go dive here, but we need to do some things, extra somethings here. So, but at the end of the day, we just implemented this provide inherent inside for the remark palette. And yeah, as you can see here, it's calling store to and just writing some bytes, vec of bytes on this inherent data sector of our blocks. So just run the third case. Cool. Okay, so I refresh. Yeah, this guy is the substrate with all the pallets, so yeah, start producing blocks. Yeah, that's yeah. Okay, so now we are again producing blocks, but if we check the blocks, we got this new section with data. So it's coming from this store to that we just created. And yeah, as we can see, we have no data here, so we just created a way to set current is another extrinsic that we created. So this is to inherit data. So yeah, let's just send it. And from now on, I mean, from the block 15 on, we will get this data from the remark palette storage and put on every and each block. So block 16 should have this new content here. So yeah, it's a way to have custom data there. But yeah, again, be careful because we have the last and final case. What if we just add an invalid inherent data? As you can see here, I'm sending an empty vec of bytes, and we have this ensure that if the remark that's coming is empty, we just throw an error. So let's just run the final case. Okay, again, the node is spin up. So okay, so not yet. And yeah, as just a heads up that we have some piece of code to check if the inheritance data is ready, is valid. But of course, we must be like very cautious here about it. So as you can see, the node is running, but we see no blocks. And that's expected because the blocks are not being validated due to this inconsistent. And I'm just proceed here. So we can see that mandatory inherent extrinsic return error block cannot be produced. So this is why we need to be very, very cautious. And yeah, write a good test around it. And yeah, so I think I can pass it on to Abhishek. And that's it. Oh yeah, by the way, last thing is just like when I implemented this, we decided the check inherent was just return okay always. So that's why we just screw the network. So yeah.
All right, hello guys, and thank you, Arthur, for that wonderful demo. Um, so Arthur pretty much covered all the fun bits of breaking inherents and adding your own. So I think that was very instructional. Next, I'll be walking you through the code of palette timestamp. So in the substrate repo, if you go under frame, you'll find the list of all palettes, and we'll look at timestamp today. So I'm in source librs, and if you're familiar with the general architecture of a palette, we have this frame support macro on each module that we want to call a palette, and then we have attribute macros like palette config and so on for storage and hooks and other things. So you may see two new things. You may see palette hooks because timestamp does use make use of hooks, and you may also see something called palette inherent. So that's not something you would commonly find in other palettes. So let's first look at frame system config. So right off the bat, we have type moment. Now, moment defines what it says it does. It just defines a moment in type, and usually for most chains it's a big number. So anything that can represent a Unix time. So it's U64 in our case. If you go to the node template, it will be U64. And we have some interesting trait bounds here. So parameter, it allows you to use it in a function parameter, default, at least 32-bit. But the one that's interesting here is scale. Now, scale allows you for arithmetic multiplication and division. We'll see why that is necessary, because uh, you need you need to perform certain divisions or multiplications in moment to obtain the block number, the current block number, and that's something that's used in the consensus system like Babe and Aura. So we'll see how that's used. Now, the second part is on timestamp stem. So this is some kind of object that will basically get a notification back from palette timestamp updating on updating certain on updating the timestamp of a block. So this is usually a consensus system like Babe or Aura. So there was a block, and now Babe requires the current time, so it will be notified by this time. Then we have a minimum period. Now, this type defines the minimum period between blocks. And this is used in a lot of calculations that goes on to palette timestamp. And so basically, these three types are all that palette timestamp works with. And we'll see in the code shortly. Now, there are two storage items now, which is a storage value that takes note of the current time. So it's also a t moment, as you can see right here. And then we have a did update. So on each block, you need to the code changes this to true. So yes, it is something to say to other parts of the code that yes, the timestamp was set. And now we get on to hooks, but I want to defer this. But okay, let's see. In on finalize, so basically, what are hooks? Hooks are parts of certain logical steps that you want to take when certain conditions are met. There is a hook for on runtime upgrade, which allows you to take certain actions when there's a runtime upgrade. There's a on initialize, which you can see right here, and that is when you want some logic to execute when your block is being initialized. And then there is on finalize, which we'll make use of here. And what this is basically it checks if did update was set, and did update will be set when the timestamp is set. So uh, if this doesn't happen, then there will be a panic in terms of Rust panic. So yeah. Finally, let's look at palette calls. So all callable extrinsics are annotated by palette call, and this palette just has one, that is set. So let's look at the code here. You may have seen that all palette calls have something called ensure signed, but palette timestamp is different. Palette timestamp has something called ensure none, and what ensure none means is no signed no signed transaction can actually call into this extrinsic. It has to be no signer at all. So the thing is, if you go to the origin time origin enum in substrate, you'll find three types there. You'll find the pseudo type, you'll find the signed type, signed user type, and you'll find the none type. And the none type is reserved for inherents, basically. So this extrinsic is called via the inherent that we'll visit shortly. And now it just checks if there is some logic regarding if it was set or not, and it takes the previous timestamp, and then it does some checks here, like it was the previous zero. Like when would the previous timestamp be zero? It would be zero in the case of Genesis block. So uh, in the case of Genesis block, the storage. So whenever you see self now, think of it as this storage right here, because you can see it has a getter defined as fn now. So self now is basically referencing this storage item. So that's the value being looked at here. Now, what happens on set? Three actions happens on set. On now, you update it with the current time, which was passed as a parameter to set. So whatever was passed as now gets updated in the now storage value. Did update gets set to true, so that when your on finalization logic runs, this check passes. Take basically is something akin to an option take in Rust. So what a take does in options is it takes the value and puts a default. In this case, the default for a bool is false. So it will reset the did update. So whatever pallet you ascribe to this type during your runtime configuration will get a notification that, hey, pallet, the timestamp was set as now. So three actions, and let's see how this is called. So this is the thing about inherent. So this is the thing about inherent. So we call it using inherents, and I've wrote some comments here, but in a nutshell, inherents are transactions that are included by the block author in each block, and they may not be enforced by other block authors, other validators, but they, in this case, in the case of timestamp, they are checked. So the validators do check if the timestamp is strictly increasing and within a certain delta. And for that, we have the provide inherent trait. So let me just quickly read it off here. So inherent transactions are sometimes referred to, okay, I already said this. Each validator decides on which inherence it wants to attach to its block. All data that is required for the runtime to create inherence comes from inherent data. Now, this data type is actually providing the runtime module, in this case, our Pallet, with the data. In this case, it would be the system time. So let's imagine you are a validator and you want to include the timestamp. Where do you get that information from? You get it from your system. And so that thing is attached within this type. So this is basically a blob of bytes. It's actually a map. So a map from inherent identifier, which is in this case maybe the name of the pallet, so maybe timestamp, to some information, and that information in this case is the time obtained from system. I'll show you shortly where this inherent is getting its data from. That's in another file, that's in the node file. So and for that we have, like in substrate, if you see substrate code, there is this concept of use traits for everything. So anything that can provide data to this inherent data type implements inherent data provider. So this in the runtime modules need to implement provide inherent. So if you're a pallet that wants to use inherents as transactions, you implement provide inherent. But your source of data implements inherent data provider. So that's a crucial step to keep in mind. Now, a module can also just check the given inherence, like I mentioned. You may check it, you may not check it, but usually you check it in for non-trivial inherence, yes. And Yep. Let's look at the code for provide inherent. Now, it's simple really. What provide inherence does is it takes this inherent identifier, which was the key to the map of bytes or the inherent data that we would be including. It takes an error which comes from SP timestamp. Now, whenever you see SP prefixed modules, they are substrate primitives. So in substrate primitives, there is this inherent error defined for timestamp. If we quickly jump to it, you can see it has just two variants. It has valid at timestamp, which is something called a non-fatal error, and it has too far in future, which is a fatal error. So we'll come back to these types. But now let's quickly go back to create inherent. Now, if you imagine from the perspective of an inherent, what needs to happen? There are producers of inherent and there are consumers of inherent. Producers of inherent will obtain their data from the outside world, from their node, whatever place. They will package that data, they will include it in the block, and they will send that block to everyone in the network. Consumers of that data who have this provide inherence for the same runtime, they will also have this code in their runtime. They will use this function called check inherent, and they will receive the call, that was the call meaning the inherent extrinsic that was included in the block, and they will also get some inherent data from their nodes. So in this case, you will you have to take a step back and imagine what is the problem that we're trying to solve. We are trying to solve the problem of syncing everybody's clocks, and if everybody's clocks is a bit different, everybody must at least be able to look at their clock and say, okay, this block has time that is within my margin of error. And that's basically the logic of check inherent. And let's just quickly look at the code where this call is being set. So let inherent data takes the inherent data that was provided by the node. It does some scale decoding. It checks if it's not empty, and just casts it into a t of moment. So it just does a casting operation right there, because remember, it's coming from arbitrary data down to your t moment type. So we have all these intermediate steps right here. Then you want to propose a new time to set in the block, and for that we use the maximum of either the system time or the self now, which was, remember, this timestamp in the storage, so the last finalized block timestamp, and the minimum period, which was the minimum period between blocks. So we take the maximum of these two. So we'll all be, obviously, since we are the validator, we'll prefer our system time. So we'll take the maximum of these two and we'll call set. Call set meaning the pallet call right here. We'll call this function, this guy, with now, and that would update the now value, and that will set it in the block using code that's not shown here. It's not really obvious here how that makes it through the block, but it's in the runtime API through a block builder, through the block builder API. So if time permits, we'll go through that as well. So now that step is done. Now you have produced a timestamp. Now what happens? Now you switch roles. You become the consumer. You receive a block from the network and you have to check whether it's within acceptable limits. How do you do that? Well, you define a delta. You say, okay, block, I am defining a 30-second, this is in milliseconds. I'm defining a 30-second delta. So if I receive a block that has more than 30 seconds of drift, I will deem it as fatal. It's not worth importing, and so I may not vote on it. But if it's within a range, if it's more than minimum period, which is allowed by my runtime, but less than that delta, then I'll say yes, I'll import that block. And so we'll receive that time from the call that was passed here. Remember, this data is coming from the block imported. So I'll just quickly annotate it. This was imported from the block, and this is coming from the local node. And then we'll obtain those values here. We'll deserialize the data into local data. And then we'll calculate the minimum. So what should be the minimum according to us? We put that in a variable, and then we'll use certain checks. So just ignore this code for now. I'll just delete this for now. So if it's more than our delta, if it's more than our what our local delta says plus the margin of error, we straight away reject it as too far into the future. We won't accept it. This is a fatal error. And uh, else, if it's less than minimum, then that means we can't really accept it because it's not really it goes against our rules. It goes against the minimum period between blocks. So receive t cannot be less than our minimum, which we calculate here. And so this is a non-fatal error, meaning we won't stop checking for inherence, but we may keep this block around the transaction pool for some while. Otherwise, if it's equal, because that's the only option left, we return an OK. And now we get back to the fatal error thing. So this is the implementation for is fatal error. And you can see valid at timestamp is false, but too far in future is true. So this is a fatal error, this ain't. So, and finally, there is this trivial call that does what it says it does. It just checks if it was a call set, which is the only extrinsic within our Pallet timestamp. So yeah. Next, we get on to private helpers, or maybe not private helpers, but something you can see these are pub functions. So other pallets, like pallet staking, for example, can call into your pallet using this get function and get the current time. So pallet timestamp is basically acting like a clock, a wristwatch for your blockchain. And using this get function, you get the current time without having to worry about what the current time is. And set timestamp is again a test function. It does basically what set would do, but in a different, in the same way, but it's meant to be used for tests only, and it's feature gated. So you can't accidentally use it on a live chain. And then we come to time. Again, uh, pallet staking would require something that implements time. You won't directly call into pallet timestamp. You would call into something that implements time. And this is the same code as what we saw here. So yeah, it's really the same code twice. And now finally, we reach down to Unix time for pallet. So Unix time will just take your now value, it will turn it into a U64, and it will get it back. So whenever you make chain state queries, you get it in a Unix time format, which is a long string of numbers. And that was it for Pallet timestamp. Now I'd like to show you where this inherent data is getting into our runtime module. And for that, you need to jump to the service file. So in the service file, you'll see we define import queues. Now, import queues are something like, it's the mechanism for how you build the block import queue. And basically here you create this inherent data provider, which also comes from SP timestamp, and you use from system time. Now, I'll leave it to your imagination to figure out what this means, but it's a system time. And then we just, I think I had seen it somewhere, but timestamp, let me do, okay, it does, okay, yeah, it does send it back right here. So it does send it somewhere in the import queue. So all we do is from system time gets into the import queue, which then acts as our source for data. And now the final piece, how are blocks being built with inherent data? For that, you need to jump to the runtime, and you need to go to something called impl runtime APIs. And so basically, impl runtime APIs are the interface between your WASM runtime and your substrate node. So you can imagine, like, since we are fetching time from the substrate node and pushing it to the runtime, we need this impl runtime thing. And that's where we get to block builder runtime API. And here there are two functions: inherent extrinsics, which creates the extrinsics that you can think of as hydrating the inherent data, provider, and check intrinsic inherence does the opposite thing. It would call into the modules check inherence from provide inherence, and it will run that code that we saw earlier. So that is, in a nutshell, all of Pallet timestamps functionalities. One final thing is I'd like to show you on timestamp set. So in configuration for Pallet timestamp, you can see that on timestamp set takes babe. Now babe right here is the Pallet babe, and babe will use the minimum duration period that is set in Pallet timestamp as a configuration parameter to calculate the expected block time. So if you can imagine, you have a 3-second minimum period. What babe uses is actually twice that to allow for a more margin for block producers to propose their create and propose their block to the network. And in Aura also it's used in the same way. So if we can jump to Pallet babe, just a second, I'll show you the relevant place where this is happening. Okay, I might have to take this route. If we go to babe, and we'll just say on timestamp set. Yeah, right here. Right here you can see impl on timestamp set for Pallet. So it takes the moment from our notifications. Remember, Pallet timestamp was sending it on every hook. So it takes that, it uses it to calculate something called a timestamp slot, which is basically the block number, because moment is of dimension time and slot duration is also of dimension time. So they cancel out, giving you a scalar unit. And finally, you assert that current slot, which is in storage. So the current block number is the same as the timestamp slot, which you calculated using time. So if you take the current time and you divide it by the minimum time period, you should get the number of slots or the number of blocks that have been on your chain. And you pass this check every time in your in babe and also in Aura. So that's how on timestamp set was being used. And yeah, that was it for the presentation.
That would wrap up our session for the day. Thank you, everybody, for tuning in.